Hello, and thank you for joining me. You're here with Data Science Teacher Brandyn, and we're going to go over how to build the feed-forward network with TensorFlow, the sequential model. So we're using TensorFlow, imported as TF, and we'll go tf.chars.sequential with capital S, and then inside we'll put a list of our layers, and we're going to do a feed-forward network. It is still a simple network, and the concept of this network is that it's going to be just essentially straight through. Yeah. Okay, so we're going to do 40, 40, and 40 neurons, and I have, just to kind of make it as classic as possible, there's 40 features in our data set, and I'm just going to run it through 40 all the way through our neural network. Okay, activation set is sigmoid. I could use sigmoid as that's maybe more than a classic way, but I set the ALU, so exponential linear unit, and then tanh as as the other layers in the network. Okay, I set the input as the second position of the dot shape. That just makes it a little bit more organic if you're going to be changing stuff in your data set. Note that I did put this in as a list, though it's inside square brackets. This is just because input shape expects a list or a tuple. Okay? It's expecting 40, and then it's going to be 40, 40, 40 all the way through, adding a little bit of a change of the activation layer, and then one, we're predicting a regression problem. So we're doing one output layer, which is the natural form of neuron. It just essentially is a linear regression in its natural state. Okay, so the loss is the mean absolute error, and the optimizer is the standard gradient descent, SGD, which is kind of maybe more like the classic optimizer, I guess you would call it. It works pretty well, though. It's a good general optimizer. Then we're going to do, after we build and compile our model, we're going to go tf.chars.utils.plotModel, and we're going to put our model inside and plot a two-file model just to save it. If we wanted to save it in here, it would show up right here, model, under your folders. Shows up in there just in your collab. And here, it's going to, I turned off the activation layer to get a little busy if you do that, but you can see here our feed forward, just the input layer, hidden, hidden, hidden. We have a pretty small feed forward network, but still a feed forward network. And just to show it in its form, I guess the simplest form. Here I changed it for 50 epochs and got down to a loss of our mean absolute error 20 with an error on our validation set of 24. So a little bit bigger. No, I didn't train it for too long, but let's see how it looked over the epochs, the history, plotting the history. You can see here, kind of probably was fit maybe 20 or 30, somewhere in between there. We could say it didn't really learn anymore. It wasn't really training anymore. And we can see maybe the learning rate was a little bit high by the validation bouncing around. Maybe we're so plotting the loss, we've got 24 on the training and 24 on the testing set. So kind of, not overfit in any sense, but really I would be concerned about the fact that we kept training it well after it was fit by. So we have to be a little bit conscious of this. Just to evaluate this, because this was, looking at the history is super important, but the next thing I would want to do, because this is a regression problem, I would look at a residual plot. So I'm going to go model.predict, but the test, just looking at the test set right now, putting the Y prediction in there. I'm going to go SNS resid plot, and I'm doing TS. I'm going to do pred, and what I'm doing is I'm selecting out the first column, because what this does is this puts in a column vector, which doesn't sound like a big deal, but in linear algebra it does matter. And so we're putting in a column vector, and so I'm selecting all of the rows, comma, and then the first column, which all there is related to it. And I'm going to set the scatter plot KWS, the keywords for the scatter plot controlling the arguments underneath. We're going to set the alpha to 0.4 and the size is a little bit bigger. Just kind of plot it out right here, and we can see we're not making too many errors. We make some errors on the outside, which is probably due to the simplicity of our error. We're missing definitely some stuff as we get to the more extreme values on our predictions. We're definitely missing, but we're not super bad here. We're getting to get good predictions overall. Okay, and so really just to highlight, adding more layers doesn't help much. So we went from a pretty small layer to maybe a little bit bigger than a super small network. So this is only adding, now we have 6 layers. So I just copied the same style, so sigmoid, ALU, tan, and then just doing one output there. So just to kind of show everything is the same. And we can see it does make a difference, but not a huge amount. So we got down to 18 or 19 for a training test. So still not overfit, and we reduced our score a little bit. Overall, this did help in this problem, and that was because we went from so simple to a little bit more complex. And this is, if we added another 3 layers, we would probably find that this does not improve very much. So as we keep increasing layers, it it doesn't instantly help for most problems. Okay, so it can help. 1 or 2 layers can help. And we saw that 3 layers did make a little bit of a difference, but as we kept adding layers, we would see that the difference that we keep gaining is quite small. Okay, well, thank you for joining me today, and I'll see you next time.